Hello guys, welcome to my world of physics infinity. Physics of the charge ring. There is a ring of radius capital R and it is given a charge Q which is uniformly distributed on the complete periphery of the ring. The center of the ring is O. The radius of the ring is capital R. And the axis of the ring is, of course, perpendicular to the plane of the ring. The ring lies in the plane YZ. YZ. The ring lies in the plane YZ. And along X and minus X. So along X-axis I can say is the axis of the ring. What are we going to do? First of all, I'll brief you about the different details, the parameters, the electrostatic parameters that are associated with the ring, the potential, the intensity, and so on. And then we'll talk about the oscillation of a charged particle in the field of the ring. So here we are. If this is a ring whose plane is in the YZ plane, X is along the X-axis, charge Q uniformly spread over 2 pi r, so it has a linear charge density lambda Q upon 2 pi r that is constant. The potential at the center of the ring, is KQ upon capital R. Obviously, if you take a small element dq and lambda is constant, so dq, k dq upon r, k dq upon r, k dq upon r, you take the contribution. So the potential at the center is kq upon r, kq upon r. Now I take a point P on the axis of the ring, distance x. So I take a point P, so where OP is equal to x, I can write here. So OP is equal to x. Then the potential, very easily you can calculate, you must have done that in your normal study of the class 12 syllabus. Okay, it'll with a simple integration, it'll come out to be kq upon x square plus r square to the power half, a small element, and then at a distance x square plus r square to the power half, and every element is equispaced, so you get the net potential at Vp kq upon x square plus r square to the power half. Well, once you have got the potential, you can take E equal to minus dV by dx. You can take the derivative of the potential with respect to x, and easily you will get the answer that EP arrow will be kqx upon x square plus r square to the power 3 by 2. Derivative of this with respect to x straight away gives you this result. And if the ring is positively charged, then certainly the field will be away from the ring, so I put it I cap. So it is along the positive x-axis. If I talk about the center, at the center, for every element dq, there is an opposing element dq here, and the vector wise the field gets cancelled. Well, even if you put the expression in this expression x equal to 0, if you put x equal to 0, then you will get EP equal to 0. So field of the ring, charge ring of course, at the center of the ring is 0. Then we can go a little further like where is the maxima, where is the maximum intensity, but I am not interested in the details of the electrostatics of the ring in this particular video. My focus is mainly on the oscillation of the particle, of a charged particle in the field of the ring. So I'll confine my focus on that particular issue. So here you are. If I take a charged particle of mass m, and having charge q naught, and I place it at the center of the ring O, then center of the ring intensity is 0, so the force on the charged particle would be 0. This means I can say that the charged particle placed at the center of the ring in the field of the ring is in equilibrium. Net force 0 is a condition of equilibrium. Fine. This is, I can also call as the mean position, but I will use the word mean position in the case of the oscillation. Right now, let us say this is the equilibrium position. So I can say the center of the ring is the equilibrium position. Now, if I disturb the charged particle Q naught by small distance x, then obviously the ring intensity is along I cap, the charged particle is positive, so it will get an electrical push forward. The ring is going to push it, the field of the ring is going to push it forward. The particle is not going to come back. This is the case of unstable equilibrium. This is the case of unstable equilibrium. I'm not interested in this situation because in the case of unstable equilibrium, there is no question of oscillation. If there is no force acting towards the mean position, towards the equilibrium position, well, where is the possibility of the oscillation? So forget about it. I change the scene. Now this time my charged particle of mass m has charge minus Q naught. Charge minus Q naught. I place the charged particle at O, net force 0, equilibrium. So this is, I can say now, the position of equilibrium. I displace it slightly along positive x. Then of course the ring has field here, field direction here along I cap. The charged particle has negative charge, so it will experience a force against the field. That means the force acting on the charged particle will be towards O. And in vector wise, it is minus Q naught EP I cap. The resultant force acting on the charged particle is towards the equilibrium position. This is the case of stable equilibrium. This is the case of stable equilibrium. Now, if it is a case of stable equilibrium, I can think of the possibility of an SHM. But for that, well, I have to make sure that the restoring force is a constant multiplied by x. The restoring force should be a Hooke's force. So, what I do, in any case, in all problems of SHM, the displacement from the mean position or the equilibrium position has to be very small. Whether it was a pendulum or a spiral spring or the floating U tube or whatever problem of oscillation that you encounter in your discussion of the oscillation, this was one of the principal conditions, that the displacement from the mean position should be very small, because only then the Hooke's law or the Hooke's force condition will be satisfied. Now in the slightly displaced position, I work out the force acting on the particle. Okay, so that will be the field multiplied by Q naught. So Q naught multiplied by the field of the ring, KQX upon x square plus r square to the power 3 by 2. And the direction of this force is towards O. So I don't put a minus sign, there is no need. I've already called it as a restoring force. It's trying to restore it, and that is why I'm calling that in the case of stable equilibrium. Now, if x is very small, in this expression, if I put x to be very small, then x square is neglected compared to r square. So x square in the denominator is gone, and x is very small, and then all this becomes, look at this. So the restoring force, there's no need to put minus sign here because I'm already calling it as a restoring force. The direction is towards the mean position, that is O. The magnitude is Q naught upon R cube times x, but all this is a constant. So restoring force is a constant multiplied by x. This constant capital K slash, well, that's my way of saying things. I'll call the Hooke's constant as capital K slash. So this K slash, the Hooke's constant, is Q naught upon R cube. Of course, the small k is 1 by 4 pi epsilon naught, the electric field constant. So constant multiplied by x. Now this is a Hooke's force. So in the displaced position, the restoring force is a Hooke's force. So it is a case of SHM. The particle about O, so this was the ring, so about O, it will do this. And because Hooke's force, the restoring force is the Hooke's force, so it will be executing SHM. And for that, straight away, you can use the condition that the angular frequency of oscillation will be the Hooke's constant divided by m. Hooke's constant, that's the simple technique of solving all the analysis of all oscillation problems. The Hooke's constant divided by m under the root. Under the root. So omega is Hooke's constant divided by m under the root. Well, I just replace the Hooke's constant as small k q q naught upon r cube divided by m, of course, is there. So this is angular frequency. Then angular frequency is 2 pi upon time period. Time period I denote by tau or t. Okay, the time period t is 2 pi by omega. So this will become 2 pi m r cube upon small k q q naught. You can crack small k as 1 by 4 pi epsilon naught and you get the answer. So here we notice that the negative charge particle placed at O is in equilibrium, but slightly displaced. It has a restoring force tendency to come back to the equilibrium position. There you conclude it's a case of stable equilibrium. Then we investigate the stable equilibrium. We find that the restoring force, the magnitude of the restoring force is a constant multiplied by x. That constant is the K slash, capital K slash, I call the Hooke's constant. So the particle is executing SHM. There you are. And we have found the angular frequency, the time period of the SHM. I hope you have liked the video.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.